So we've had rather a silly example about beards and male and female. I quite like male and female because the hypothesis and H and H bar are quite easy. Now I'm going to do the left-handed, right-handed thing, and we'll see a slightly different message. Let me write it out again. The probability of your hypothesis given your data is the probability of your data given your hypothesis, P of H, over P of D given H, P of H, plus probability of D given H bar, P of H bar. Bayes' theorem. And now, your data is that the person is left-handed. And we'll see what happens. And H is that the person is male. So now we've got the probability that they're male given that they're left-handed. I might be working out, I don't know, some marketing thing for left-handed knives or something. Probability that person is male given that they're left-handed is the probability that they are left-handed given that they're male. And you can imagine yourself working out this because you can get a whole bunch of blokes and see which ones are left-handed. Times the probability that they're male over the same thing, probability that they're left-handed given that they're male, probability of male, plus probability that they're left-handed given that they're female times the probability of being female. Well, let's just make some numbers up here. So the probability of your hypothesis given your data is going to be equal to, let's say, 0.1, because 0.1 of males are left-handed times 0.5 over 0.1 times 0.5 plus probability of females being left-handed. Let's just say that's 0.1 as well times 0.5, and that's pretty obviously equal to 0.5. So we've got this rather peculiar case here that the extra data, and that equals P of H, which is 0.5. We've got this rather peculiar case that P of H given D equals P of H. So the data makes no difference. Your data is that the person's left-handed, and purely because these equations cancel out, because this equals this, we've still got a 0.5 down here. Yes?
I know it sounds so. Do you mind not skipping that step and maybe put on the...
This one?
Yeah, the one that's in between the two formulas? Maybe like substituting...
This one?
Yeah, substituting...
This one to this one, yeah?
Yeah.
Let me draw it in a different colour. I'm just evaluating it. This is 0.1, which is that.
Yeah, I know. But can you maybe put 0.2 times 0.5?
This one.
Yeah. Where the D's and the H's and things like that, just what your time is.
Yeah?
How did you evaluate that at 0.1?
That is because about 10% of males are left-handed. It's the probability of your data, which is that you're male. Sorry. It's the probability that your data, which is that you're left-handed, given that you're male.
Yeah.
So I'm saying 10% of men are left-handed.
Okay, so you just saying that's the value.
That was what we had before the break, yeah? Wasn't it? 10%, I said?
You're just pulling it out of thin air, though.
Pretty much.
That's what you're saying.
Yeah.
Okay.
I'm just using it as an example. You can put different numbers in if you want.
Okay.
Yeah, the actual numbers don't make any difference. You can put anything in there, but these are just examples, just to show you how the numbers pan out. So what you're saying is that the probability of H given D equals P of H. Data makes no difference. We can evaluate this using probability. That's the law of conditional probability. The probability of A given B is probability of A and B over probability of B. Yeah, that's the conditional. And I can rephrase this equation here. So what we have there is a statement of independence. The statement of both statements happening, both things happening, both H and D happening together, is the product of them happening separately. So what we say here is H and D are independent. That's what that means there. Or this way is a better way of thinking about it. Depending on what H and D are, sometimes it's easier to think about the product rule, sometimes it's easier to think about the conditional product. That's a multiplication, yeah, times. That's a times. So what does that look like if we translate? So I'm saying that the probability of male given left-handed equals the probability of being male. So it doesn't matter if you know they're left-handed or not. Left-handedness is not, it's got no connection with gender at all because of this statement here. Or the probability, if I go down to this one, of being male and left-handed equals the probability of being male times the probability of being left-handed. They're both the same statement. All I've done is use the conditional probability law, but they've got slightly different flavours or different fields to them. Okay. Now I'm going to introduce the notion of prior and posterior probabilities. I'm going to give you a nice example which occurred to me the other day. I was in a cafe having a cup of tea with my daughter, who's 8. And it was,
Hot chocolate.
she had hot chocolate, I had coffee. And we were wondering what proportion of people would be carrying an umbrella. Because it was raining, we were having a cup of tea, and there were people walking past us on the street with umbrellas. And I said, it'll be about 50-50. Prob of an umbrella equals 0.5. That's my hypothesis, R for Robin. Here's Annabelle's probability. She said 3/4 of people will be carrying an umbrella. And I'm going to assume that one of us is right here. We'll clarify that later on in the course. But for the moment, I'm going to say that one of us is right. The real probability is either that or that, but we don't know which, and we're arguing about it. Okay? Now we have some data to bring to bear on this, yeah? We've got 20 people that we counted, of whom 14 had an umbrella and 6 had no umbrella.
For the sake of my notes, so I don't get confused, can I just call them H1 and H2?
Yes,
Okay, so
you can call them what you like.
yeah,
You don't need to follow my notation at all.
but HR and HA, I'm going to get lost.
Let me write out Bayes'. So I'm going to call that H, and I'll call this H bar. I might change my notation back anyway, but let's just write out Bayes' theorem. So I'm interested in this. Probability of H given the data. And this is quite a subtle process. There's quite a lot going on here, and it's philosophically, I won't say suspect, but there are very clever people who say, this is complete nonsense. You cannot do this. This is crazy. And there are equally clever people who say you can't do anything else. This is the only way to apply mathematics to this problem. So it's a controversial. This is controversial.
Sorry, Robert, can I ask something really quickly? Shouldn't h plus h bar equal 1?
Yes.
So did you say that the 0.5 is h and the 0.75 is h?
Oh, no. The question was, shouldn't h plus h bar be equal to 1? And we've got a half and 3/4, which add up to more than 1. Let me rephrase this. Let me say my hypothesis is that p equals 0.5, and Annabelle's hypothesis was that p equals 0.9. That's all right, isn't it? We don't know which of these it is. She says nearly everyone's got an umbrella. And I say only half have. And I could say 0. These don't need to add up to 1. You've got to keep your wits about you as to which, yeah?
So you're not labeling your hypothesis H and his H bar?
No.
Okay, sorry.
Well, I am here. But h is 0.5 and h bar is 0.75. We just don't know which is the truth. That's all. Let me write out Bayes' theorem. Let me write out Bayes' theorem and we'll talk about it. Probability of HR given the data equals probability of the data given HR, P of HR, over probability of D given HR Oops. That's not good. All right. Now we need to fill these in. We need to fill these in. What was the data again? The data D was 14 and 6. That's umbrella and no umbrella. That was the data, wasn't it? I'm going to introduce a new idea. What I'm going to do is say P of HR equals the probability that HR is true. And the probability that HA is the prob that HA is true equals 1 minus HR. 1 minus the probability. Okay? Because in this fictional world, I'm assuming that one of us is right, and I just don't know who. So she might be right with 90% probability, but I might, if that's the case, then I'm right with 10% probability. There's two probabilities. There's a probability of carrying an umbrella, and there's a probability of correctly saying the proportion. Okay? These are before looking at the data. Before looking at the data. Before looking at the data. These are called priors. And I'll spend a little bit of time talking about this. Now, you'll observe that I'm 46 years old. Maybe you can't observe that, but it's true. And she's 8. So I'm a grown-up, and I've been around for a long time, and I've got quite a lot of experience about umbrellas and how many people have umbrellas, and I know roughly how many people have got umbrellas, and I know what it's like to walk and forget your umbrella and all sorts of things. I've got lots of experience, I've got lots of knowledge, and I know what I'm doing. I'm probably right. And she's just 8 years old. She hasn't got the faintest idea. She can't even spell umbrella. Who's going to be right? Me or her? It's going to be me, isn't it? There's quite a lot going on here. This is what you call prior probabilities. Equals opinions, hunches, social knowledge, the technical word for this is a subjective prior. Or an opinion. It's non-specific, it's personal, it's psychological. I don't have to justify it, it's just that's what I think. If I'm arguing with a little girl, I'm probably right and she's probably wrong. But, and we'll cover this later in the course, it's not absolutely likely that I'm right. She might have been doing a school project on umbrellas. She might have some data which I don't have. But probably I'm right because I'm a grown-up.